Yeah, I'm going to do this on next blackboard. I'm going to erase everything with this right here, with this ugly piece of dust. Ugh. Good morning, fellow mathematicians. Welcome back to another video. Today we are back with an integral, and this is going to be another Papa's improvised session. You see, a boy sent me this through Twitter. I hope you can actually see it. And yeah, we are going to dive right in. He wants me to solve this using the residue theorem. I'm going to try my best. Maybe I'm going to suck. Maybe I can actually do it. We are going to try it out. Let me write it out, actually. Okay, so here's the idea I have. We are dealing with a sign right here. So why not introduce a complex valued function? So we are going to call this thing I right here, actually. And one thing I'm seeing is that this right here is an even integrand. You see, if we plug negative x in, yeah, this is going to stay positive down here in the denominator. Here in the numerator, this is negative x. Sine of negative x is just negative sine of x, so this negative sign is going to cancel out. So we could actually express this as 2 times the integral from 0 to infinity of this integrand. But I don't know if this makes actual sense. We are just going to define ourselves a complex valued function. Let's call it f of z. And it's going to be equal to, yeah, let's just take the usual ansatz. So z times e to the I z over z to the 4th power plus 1. What contour should I use? Well, I would like to make use of Jordan's lemma in the end, meaning in the upper hemisphere, in the upper part of the complex plane, a semicircle would vanish. That means we are going to take a look at this very contour right here. That's our contour C. This is our gamma, and it's going from negative r to r. I'm pretty certain that this is going to actually work. Yeah, we can use Jordan's lemma on this later on. So why not factor this right here a little bit, this denominator, to see what poles are actually in here. So you see, we don't have any singularities, so it wouldn't explode to infinity unless we would plug in infinity actually. So why not factor this? 1 is nothing but negative I squared, so we can actually factor this because this is z squared squared. So this is z times e to the I z over z squared plus I times z squared minus I. Now we need to find the zeros of this thing right here. This is actually quite easy. So we are going to get 2 zeros, set 1 and 2, exactly at, well, we have this being equal to 0, so subtract I on both sides, for example. Yeah, then take the square root, so positive, negative square root of negative I, but negative I is nothing but I times square root of I. So this is going to be a positive and negative I times square root of I. Same spiel here, just this time without the negative sign is in the square root. So set 3 and 4 is going to evaluate to positive and negative square root of I. Okay, this actually sucks a little bit because we have 4 values now. Well, we have a 4th degree polynomial right here, so we need to get 4 roots actually. So let's find out which of those values are actually up here in our contour. I'm going to take an algebraic approach. I don't know. So let's see, I would like to do this. That's a bit easier. Let's say we have some complex number z being equal to square root of I, meaning z squared is equal to I. In the end, this just means we are going to find some a plus I times b squared being equal to I. Okay, you can also use polar coordinates, but I'm going to use this because I want to annoy Thematica. Because he has the opinion that everyone who's using algebraic approaches to something like this right here should burn in hell. I agree with you, but it's still fun. Algebra is always so cool. Okay, let's see. We are going to get yeah, a squared minus b squared plus 2 times I, a times b, being equal to I in this case. And now we can just compare the real and imaginary part. You see our real part on this side is 0, meaning a squared minus b squared must be equal to 0, meaning equivalently that a must be equal to b, the absolute values. I'm just going to take a look at the principal branch. So a is equal to b. If we plug this into here, yeah, we are actually going to get that, well, this part must be equal to 1 because the coefficient of I is 1. So 2 times a times b is nothing but, with this plugged in here, let's say this is 2a squared must be equal to 1. Dividing by 2, it's not equal to 0. If you trust the piano axioms, a squared is nothing but 1 over square root of 2. Meaning equivalently that we can take the square root. A is nothing but plus minus, yeah, I'm sorry, this is 1/2. I was thinking ahead of time, and if we take the square root, this is plus minus 1 over square root of 2. A is equal to b, meaning b is nothing but positive or negative 1 over square root of 2. And then we have our, well, square root of I basically. So this was just a really quick derivation of this thing. So we have set free being equal to positive square root of I, which is going to evaluate to, well, this positive branch right here, you could say, or the negative one. It really doesn't quite matter. I'm just going to call it square root of I. Set 3 and 4 can be either equal to. Okay, what do we get? We are going to get 1 plus I over square root of 2. If we just plug this into our complex number a plus I times b. Or we are going to get negative 1 plus I over square root of 2. I hope you can see where all of this came from. Now it's actually quite easy to evaluate those set 1 and 2's, because we can just multiply those terms by I, and then we are pretty much done. So set 1 and 2 is going to evaluate to, okay, on the first one we are going to have either, yeah, this is going to be, so I times this one is I minus 1, I minus 1 over square root of 2, or we can have, this equal sign isn't really an equal sign, it's just going to apply to those two solutions we get. So we have negative, the same thing we had here, so negative I minus 1 over square root of 2. Okay, now we actually have our 4 values for set, and we can continue. So let's see what is in our plane. So you see we have this right here. This is definitely in our contour because 1 plus I is somewhere here with a square root of 2 factor. Doesn't really quite matter because this is positive. So this one right here is actually in there. This one right here isn't in there. It's somewhere down here if I take a look. And what else do we have? We have this right here. Yeah, this is actually in the plane because we have negative 1 and I with a certain scaling factor. This is exactly here somewhere. So we have this and this right here. And the other one is 1 minus I. This would be down here somewhere. So this doesn't work out. So we have those two values. And yeah, with that out of the way, we can actually now calculate our residues. So let's go ahead and get started. You see, this is quite some thinking I have to do. I'm not doing this on a regular basis. I'm just doing complex analysis just for fun. I've never done a course on this same thing with multivariable calculus. So every time I'm doing this, I have to get used to it once again. Okay, so you see, let's at first calculate the residue at set being equal to, positive square root of I, let's say. So square root of I being equal to the limit as set approaches square root of I of set minus square root of I times f of set. But f of set is nothing but this right here. Let's write this out real quick. So we have set e to the I times set over. Okay, so I'm going to leave this part as it is, set squared plus I, but I'm going to factor this one here respectively, because this is nothing but, you see, we have found those zeros. So we have set plus square root of I times set minus square root of I. So set plus square root of I times set minus square root of I. I hope you can see where this factoring came from. That's just factoring polynomials. When you have found out the zeros, then this and that is going to cancel out, and now we can safely use the limit on here. So we are going to end up with, okay, so up here we have square root of I e to the I times square root of I. Oh, this is going to be quite a mess in the end, I guess. We are going to see how this turns out. Z squared is going to be I plus I is 2 times I, and we also have square root of I plus square root of I is 2 times square root of I. This and that is going to cancel out to e to the I square root of I over 4 times I. Is this going to turn out as a complex number? I'm not quite sure at the moment because we are having this up here. Is this going to evaluate to a real value? We are going to see, I guess. I don't think that it can be complex. No, it can't be complex. So it should be real in the end. That's the observation we can actually take. Okay, now we have this other residue. The residue at the point z being equal to, what was this exactly? Yeah, this is positive I times square root of I. It's now nothing but the same limit basically. Limit as z approaches I times square root of I of, well, z minus I times square root of I, z e to the I times z over, okay, now I'm going to leave this part as it is, z squared minus 1, and I'm going to factor this one respectively. So we are going to get z minus I times square root of I, z plus I times square root of I. And once again, you might notice that this and that is going to cancel out, and now we can safely take the limit. That's straightforward. So we have I times square root of I, e to the I times I is negative 1, so we have negative square root of I. Oh, this is really ugly actually. This doesn't look quite good. So the residue we are going to get doesn't look too friendly. We are going to see over, okay, so this is I times square root of I. So I times I is negative 1, so we get negative value, so negative, yeah, here must be an I. I was already wondering, so I forgot the dot on my I right here. So this right here is supposed to be an I. So we get negative 2 times I, okay, and we have 2 times I plus square root of I. Once again, this and that is going to cancel out, and we are going to get e to the negative square root of I over, okay, we have this negative sign, 4 times I. Yeah, and now we can actually use our residue theorem and write out this contour. So Cauchy's integral formula. Yeah, I'm going to do this on next blackboard. I'm going to erase everything with this right here, with this ugly piece of dust. Okay, what do we have now? We have gathered that we have actually a contour integral over f of z over this closed contour being equal to 2. So we had this part of negative r to r. So I'm going to draw it once again. We had this part right here from negative r to r. This is one line integral. Actually on the real axis, so we can integrate f of x, which would be x times e to the ix over x to the 4th power plus 1 dx. And we also had this contour gamma right here, so plus gamma. And this right here is actually equal to 2 times pi times I. So this is 2 times pi times I times the sum of all the residues we have calculated. So we had this factor of 1 half, no, I'm going to write it out. So we had e to the I times square root of I over 4 times I. So this is what we have. And then with negative sign, e to the negative square root of I over 4 times I, okay? This I and this is going to cancel out. The 2's are actually going to cancel out to 1/2. So this is equal to, okay, I'm going to bring the 1/2 factor to the outside, so pi over 2, random pi popping up once again as always, times e to the I square root of I minus e to the negative square root of I. Okay, so in order for us to get our original integral, kind of, we actually need to let r go to infinity. By Jordan's lemma, I'm not going to derive it once again, just introduce a proper parameterization in here. this is going to vanish, this is going to go to 0 in the limit, and well, a constant isn't affected by the limit. So actually on this side we are going to end up with, as r approaches infinity, this is going to vanish, then we have an integral from negative infinity to infinity, x e to the ix over x to the 4th power plus 1 dx. And here's mostly the trick that we are going to compare real and imaginary part. Meaning e to the ix is nothing but Papa Euler, so we can break this up into two integrals. I hope you can see where this comes from. Negative infinity to infinity of x cosine, and then cosine of x over x to the 4th power plus 1 dx, plus I times the integral from negative infinity to infinity of x sine of x over x to the 4th power plus 1 dx. So just breaking this up into this complex number, real and imaginary part. Actually you see, this one right here was an even integrand just because the sine of x is going to turn into negative sine of x when checking this property, and this is going to be even in the end. But this one right here is going to be odd because if like negative x into here, cosine of negative x is just the cosine, so this is just negative this integrand, meaning this right here should be 0 overall because we are integrating over a symmetric integral. Meaning this one right here must be I times something in order for this to be a value of this integral. Yeah, let's see what this is going to evaluate to. This actually looks like a mess. Maybe we can do something with it. Yeah, okay, we are going to take a look what this right here actually is. I'm just going to take a look at this right now. So we have e to the I times square root of I minus e to the negative square root of I. I guess it doesn't help to break this up into cosine of square root of I plus I times sine of square root of I. This doesn't make any sense. This is going to result in something really ugly. We would actually have 4 different factors right here, and oh yeah, we had the definition for square root of I. So this is e to the I times square root of I was nothing but 1 plus I over square root of 2, and this is minus e to the negative I 1 plus I over square root of 2. Okay, and actually we can distribute this this I into here to get an I up here and negative 1 right here. I hope you can see where this came from. And actually we can break this up. So this right here, the numerator is additive. So we get e to the I over square root of 2 minus 1 over square root of 2 minus e to the negative 1 over square root of 2 minus I over square root of 2. Okay. And yeah, since the exponent is additive, we can break this exponential function up into the multiplication of exponential functions. And you see we have this common factor of e to the negative 1 over square root of 2. So why not factor this out? So this is e to the negative 1 over square root of 2 times, e to the I times 1 over square root of 2. I'm going to put it that way. Minus e to the, this is so nice. This is actually really nice. Negative I times 1 over square root of 2. And you see, just as a little reminder, if you have the sine of x, we can express it as e to the I times x minus e to the negative I times x over 2 times I. So actually, if we multiply both sides by 2 times I, it's not equal to 0. This right here is actually the sine of 1 over square root of 2 times I. So this right here is nothing but, 2 times I and sine of 1 over square root of 2. And we have this factor, e to the negative 1 over square root of 2. Okay, this is really cool. This cancelled out. I'm terribly sorry. The German boy came through for a second. So this cancelled out quite nicely. And now the printer is run. No, it's just this stuff right here. Yeah, I'm in a public room, you could say, and sometimes the printer is going to run. It's going to start on its own because someone down here is printing something, and now this marquee right here is just going up at the moment. Okay, so cool. So we have evaluated that this integral is equal to this chunk. So you see, now we can actually compare the real and imaginary part. Also, I don't want to forget the factor of pi over 2. So actually, our integral I is nothing but the imaginary part of this thing right here times this factor of pi over 2, meaning our integral I is now nothing but, so this 2 and 1 over 2 is going to cancel out, pi times e to the negative 1 over square root of 2 times the sine of 1 over square root of 2. And did I forget anything? Or yeah, I'm going to propose this as my final answer, and I hope it is right. That's quite a weird result if you ask me. So yeah, we have a random pi in here and e to the negative something irrational. So this is transcendental, this is transcendental. Sine is a transcendental function most of the time, so probably this value of this thing is also transcendental. It looks like it. Yeah, I thank you guys for watching. I hope you did enjoy this new improvised session. If you want to see more of this, I can try my best to put up more of this stuff. With this improvised session, you can follow me, go through the solving process of some integrals or problems. Not all problems go this smooth. Some problems just won't work out any good. But yeah, if you did enjoy this video, please like, subscribe, and recommend channel. If you like, you can support the channel in many different ways. Feel free to do so if you want to support the channel, if you appreciate the work I'm doing. And yeah, I guess up until the next video, no? And I'm actually clean. I haven't dirtied my t-shirt with any chalk dust. Up until the next video, I'm wishing you a flammable day, and I hope this helped you, guy from Twitter. See ya!